Hello everyone, welcome to Analysis and Design of Algorithms. In the previous video lecture we have discussed about frequency count method to determine the time complexity of an algorithm. In today's lecture we will be discussing about asymptotic notations. This is a very important chapter for calculating the time complexity of an algorithm. Time complexity of an algorithm, it can be calculated in two ways, that is posteriori analysis and priori analysis. Posteriori analysis is done on a program. So when you implement the algorithm, when you using any programming language, you run it on a machine and you calculate the time, that is called as posteriori analysis. This posteriori analysis gives us the exact time complexity of an algorithm. The next one is priori analysis, which is done on the algorithm. Priori refers to prior to implementation. So prior to implementation, which means that the analysis is done on an algorithm, and such an analysis gives us an approximate time complexity. It is not exact, it is approximate. So in the last video lecture we have seen how to calculate this using frequency count method. That is an example of priori analysis. Right? Now there is another way to perform priori analysis, and that is called as asymptotic notation. So this asymptotic notation uses a function called f of n to describe the running time of an algorithm, and where this n refers to the size of the input. So this asymptotic notation comes from mathematics. Okay. So running time of an algorithm, it falls under three types: best case, worst case and average case. So using asymptotic notations, when we calculate the time complexity, it can fall in any of these categories: best case, worst case and average case. So let's discuss them one by one briefly. What is best case? Best case refers to the minimum time required for an algorithm to execute. For example, let's take an example for linear search. You have a set of array elements. If we are trying to access a certain key element in the linear search, and if that key element is present in the very first position, if that key element is found in the very first position, then the algorithm is going to take minimum amount of time or least amount of time. So such a scenario in which the algorithm takes a minimum time is called as best case. Worst case, maximum time required for an algorithm to execute. We'll take the same example for linear search. So worst case, in terms of linear search, if the key element that we are trying to search is present in the last position, or if that key element is not present itself in this array, then we call it as maximum time required for an algorithm, which is termed as worst case. Average case refers to average time required for an algorithm to execute. Suppose there are 10 elements in an array, or say 100 elements in an array, and if you are trying to access the 50th element somewhere in the middle, and if it is present, then it is called as average case, or average time required for an algorithm to execute. So to represent all these time complexities, best case, average case and worst case, we have certain asymptotic notations like big O, big omega and big theta. Big O represents the worst case or the upper bound of an algorithm. Big omega refers to or represents the best case, that is the minimum time required for an algorithm, and it is also called as the lower bound of an algorithm. Big theta represents the average case of an algorithm, or the average time required for an algorithm is represented by theta, and it is also called as tight bound. Next we will see what is meant by lower bound, upper bound and tight bound with the help of an example. So here I have listed all the time functions. These are all the standard time functions which we have seen in the previous video lectures. So it starts with 1. This is constant time, which is less than log n. This is less than root n, then less than n, and so on. N square, n cube, then goes up to 2 raised to n, 3 raised to n and n raised to n. We'll take an example. We have a function over here, f of n is equal to 2n square plus 3n plus 2. the order of, or the highest order of this polynomial is n square. So we can say that f of n is equal to order of n square, or you can say big O of n square. So which means that all the functions which lie above n square, including n square, these n square, n cube, 2 raised to n, 3 raised to n, n raised to n, all these time functions, they represent the upper bound of f of n. They represent the upper bound of f of n. And all the time functions which lie or which are less than n square, including n square, all these, they represent the lower bound of the function f of n, and n square itself represents tight bound. So I can say f of n is order of n square or upper bound, n cube is also upper bound, 2 raised to n is also upper bound of f of n function, because they are all greater than n square, and all these functions which are greater than n square represent the upper bound. Similarly, I can write n square, root n and n represent the lower bound of function f of n. So I can use the symbol omega. Big O is for representing upper bound, so I have written O of n square. Omega is for representing lower bound, so n square, root of n, n. So all these functions are below or are less than n square, that is why I have denoted them with the help of omega symbol. Another example, suppose f of n is equal to n. Suppose f of n is equal to n, then all the functions which lie above n, n log n, n square, n cube, all these including n, they represent the upper bound, including n, and all the functions that lie below n, including n, represent the lower bound. They represent the lower bound. So since that is clear, we can move on to the first asymptotic notation, that is called as big O notation. As we all know, big O notation represents the worst case time complexity of an algorithm, or it represents the upper bound. So what is the definition of big O? It says that the function f of n is equal to order or big O of g of n. Now instead of saying order, we are going to use big O. The function f of n is equal to big O of g of n if and only if there exists positive constants c and n naught such that f of n less than or equal to c into g of n for all n greater than or equal to n naught. So we have constants over here, c and n naught. C has to be greater than 1 or greater than or equal to 1, and n has to be greater than or equal to n naught. C and n naught have to be positive constants. Okay. So let's prove this particular definition with the help of an example. I have two functions, f of n and g of n. I have to prove that this is true. F of n less than or equal to c into g of n. I have a polynomial which represents the function f of n, 2n square plus 5n plus 1, and I have gn over here, and I have taken n square. Now why I have taken n square is the highest order of this polynomial is n square, so I have taken it as n square. You can have any polynomial here that you want. So I have taken here n square. But the good thing is, or the best thing is, whatever highest degree this polynomial has, you take that as gn. C has to be greater than 0, n should be less than or equal to 1. So if we see this figure over here, we have to prove this correct. F of n should be less than or equal to g of n. It has x axis and it has y axis. X axis has n, that is size of the input. T represents, this y axis represents time. Right. So let's, on the left hand side, let's have f of n. On the right hand side, have g of n, c into g of n. So what is f of n? 2n square plus 5n plus 1. What is c into g of n? C into n square. C into n square. So let's take the value of n as 1 and let's take the value of c as 4, and let's substitute these values n equal to 1 and c equal to 4 in these two equations, and let's see if this definition is correct, or let's try to prove it right. 2 into 1 square plus 5 into 1 plus 1, and here it is going to be 4 into 1 square. Value of n is 1, value of c is 4. So 1 and n are substituted in these two equations. What will be the answer? 2 plus 5 plus 1 and 4. So this is 8 and this is 4. Is 8 less than or equal to 4? This is false. So this definition is false for values n equal to 1. Next, we'll increase the value of n from 1 to 2. So what will be the answer? It will be 19 for f of n and 16 for g of n. Again, 19 less than or equal to 16, it is false. Let's increase the value of n from 2 to 3 and let's find out if this proves correct. If we substitute the value of n as 3 and c value is 4, that will be f of n will be 34 and g of n will be 36. So 34 less than or equal to 36 is correct. So we have proved that f of n less than or equal to c into g of n. So we can say that f of n is equal to big O of n square. Under which conditions? For all n greater than or equal to 3. So when n value becomes greater than or equal to 3, f of n is big O of n square, or f of n you can say f of n is big O of g of n. If I take n value as 4, also this condition will be proved correct. If I take n value as 5 also, it will be f of n is equal to big O of n square. That is why it is written as greater than or equal to 3. So if you see this particular graph over here, at one particular point these two graphs are intersecting. So after this intersection, f of n is always less than g of n, or c into g of n. So that intersection point we are going to call it as n naught, and this n naught is always greater than or equal to n, and n is greater than or equal to n naught. So instead of n square, can I have n cube? Yes, as we have seen in those mathematical functions which are arranged in ascending order or increasing order, n cube is greater than n square. N cube is greater than n square. So I can write n cube, I can write 2 raised to n, I can have 3 raised to n, I can have n raised to n for representing the upper bound. But we have to consider the least upper bound in this case. So the least upper bound for our function f of n is n square. That is why we write f of n is equal to big O of n square. The next asymptotic notation is big omega notation. So big omega notation represents the lower bound of an algorithm, or it represents the best case of an algorithm. What is the definition of big omega? A function f of n is equal to, we can say that function f of n is big omega of g of n if and only if there exists positive constants c and n naught, such that f of n greater than or equal to c into g of n for all n greater than n naught greater than or equal to 1, and c greater than 0. Let's try to prove this with the help of an example. First example, f of n is equal to 3n plus 2, g of n is equal to n. So since the degree of f of n is n, I have taken g of n as n. Let's put values c is equal to 1 and n is equal to 1 and substitute these values in these equations. So if I substitute n is equal to 1 and c is equal to 1 in this, I will get 5 greater than or equal to 1, which is true. Hence we have proved f of n is greater than or equal to c into g of n. Let's take another example. F of n 2n square plus 5n plus 1 and g of n is equal to n square. I will put c is equal to 2 and n is equal to 1. So substitute values of n is equal to 1 in these two and c value in this. What will I get? 8 greater than or equal to 2. When I substitute n equal to 1 and c as 2 in these f of n and g of n, these are the respective values that I get. For f of n I am getting 8, for g of n I am getting 2. Here also f of n is greater than g of n. Hence we can say that f of n is omega of or big omega of g of n, which means, or you can say f of n is big omega of n square for all n greater than or equal to 1. So this represents our lower bound, n square. So can I write n over here? Yes, I can write. Can I write log n? Yes, I can write. All these time functions are less than n square, but I have to take the closest one. So the closest one is this n square. So omega of n square for all n greater than or equal to 1. So this is going to represent our lower bound. If you check this simple graph over here, after a certain point of n naught, g of n is always less than f of n, or you can say that f of n is greater than or equal to c into g of n. Here n naught is greater than or equal to 1, n is greater than n naught. Next we will talk about theta notation. So this theta notation represents the average case of an algorithm, and it also denotes the tight bound of the running time of an algorithm. Big omega was upper bound, big O was upper bound, big omega was lower bound, and big theta is tight bound. So what is the definition of big theta tell? A function f of n is equal to theta of g of n if there exists two positive constants c1 and c2, positive integers n and n naught, such that c1 into g of n less than or equal to f of n and f of n less than or equal to c2 into g of n. So this f of n, as you can see here, it is going to lie between these two functions c2 and c1, or c1 into g of n and c2 into g of n. F of n is going to lie in between these two. So that is why it is called as average case. Let's try to prove this with the help of an example. I have f of n is equal to 3n plus 2. So g of n I have taken it as n. Let c1 is equal to 1, c2 is equal to 4. They have to be positive constants. You can take here any value that you want, but you have to prove this definition correct. So I have taken c1 is equal to 1, c2 is equal to 4. So let's put this equation over here in this fashion according to the definition given, and let's substitute the value of c1 and c2. I'll take n is equal to 1 over here first. When I say n is equal to 1, c1 into g of n will be 1, f of n will be 5, c2 into g of n will be 4. So according to the definition, this is false. According to definition, this is false. I'll substitute the value of n is equal to 2. If I substitute the value of n is equal to 2, 2 less than or equal to 8 is correct, 8 less than or equal to 8 is true. So we have proved for n is equal to 2, c1 into g of n less than or equal to f of n less than or equal to c2 of g of n. Hence we can say that this function f of n is big theta of n, is big theta of n. Under which conditions? For all n is greater than or equal to 2. We got this definition correct, or we have proved this definition correct for the value n is equal to 2. Hence it is n greater than or equal to 2, c1 is equal to 1 and c2 is equal to 4. So this was about all the asymptotic notations. Thank you.